Hey guys, this is Nikhil. Welcome to my new video in fault analysis. Let's So the target audience for this course are students appearing for GATE, IES or any PSU exam. They can benefit from this course, as well as practicing power engineers, any power utility companies, and also students pursuing their BE, BTech or MTech for their semester exams can also benefit from this course. And this is me, Nikhil Nakka, presenting you this course. Okay, you can read about me, pause the video. You do follow me on unacademy.com. I'm here on Unacademy, verified educator. Okay, and there are some 8 very wonderful courses for you waiting here on Unacademy. Okay, follow my profile as well as enroll in these courses. Okay, you'll be getting timely updates about my new lessons I'll be adding in that course. And make sure that you subscribe to this YouTube channel. Okay, please subscribe to the YouTube channel. There are many more awesome courses ready to come for you. Okay, and also there shall be some bell icon like this here, and also click on the bell icon so that you'll be getting notification whenever I will be putting new videos in the channel. Okay, subscribe for more. All right, let's continue our discussion from the last video. Okay, we were discussing about classification of different types of faults that occur on a power system, and we said that there are faults are called short circuit faults and open circuit faults, which are also called as shunt or series faults respectively. So we will see how these faults are characterized. In fact, okay, how these faults are characterized. So firstly, what is a shunt or short circuit fault? Let's rediscuss about how shunt or short circuit fault occurs. Okay, so shunt or short circuit faults occur, okay, when two or more conductors or objects, okay, it necessarily need not be a conductor, it can be any object, okay, having a potential difference between them. Potential difference between them come to contact. Okay, this is the condition for the occurrence of short circuit fault. For example, there are two lines. Okay, there are two lines in a transmission line. If these both lines touch with each other, then you say short circuit fault has occurred or shunt fault has occurred. Or say a line has been made contact with the ground, then also then short circuit fault is said to be occur, because usually in a transmission line no two conductors will be having the same potential. Okay, there will be some difference of potential between them, between two lines. That is what we call as line voltage, you remember, right? And also line will be having certain potential and ground's potential is zero, so different potential, there is a potential difference is there. Then also whenever this kind of situation occur, then you say a short circuit fault is said to occur. So the characterization thing is, what happens when a short circuit fault occurs on a system? What happens is the value of current will increase. Okay, current value will increase. And what happens to frequency and voltage means they will decrease. Okay. Okay, current value shall increase, voltage and frequency will increase in case of a short circuit fault or a shunt fault. Now what happens in a series or open circuit fault? What is it actually? Whenever the line conductor suddenly breaks, okay, two or more line conductors like this, they break, then you say this open circuit fault is said to occur. And what is it characterized by? What happens to current under open circuit fault or short circuit fault? When the circuit open, what happens? The current value will decrease automatically. Okay, current will decrease, and obviously the voltage is converse, it will be increased. Okay, voltage and frequency will increase. Okay, please remember these points, very important for your competitive exams. Okay, what happens when shunt faults occurs or series faults or short circuit or open circuit respectively. And we have also discussed that short circuit faults are classified as symmetrical faults and unsymmetrical faults, and symmetrical faults otherwise called as balanced faults, unsymmetrical faults also called as unbalanced faults. And we have also seen the classification of these subtypes of faults into these two categories, that symmetrical faults or balanced fault, the three lines come into contact with each other or three lines together with ground, this constitutes the symmetrical or unbalanced fault. and unsymmetrical or unbalanced fault will have LG, okay, one line to ground or line to line or line to line and ground, okay, and these percentages represent or give the frequency of occurrence we already known. Okay, LG fault is the most frequent fault, whereas symmetrical faults are less frequent fault. When you talk about severity, these are more severe. Okay, symmetrical faults are more severe, and these are less severe. Okay, okay, and LG fault is the least severe. Okay, very less severe. Okay, and also we have discussed that how can we clear a fault. Okay, whenever we humans, when we suffering from some fault, we have medicines, we have tablets, something like that to cure, but there is no curing, only cutting, only surgery in case of power system. How do you do is by switching. You will switch off that circuit. Okay, if ever some component or any part of a circuit of a power system is subjected to a fault, then you will just cut it out from the healthy system, that is you will switch it off. So this switch, okay, switching will be done by a switch, and switch generally used to switch during the fault is called as a circuit breaker. Circuit breaker is a switch that is used to switch by switching on or off action. Okay, on or off action. Okay, that is what the switching of fault is done by using a circuit breaker. Okay, and the circuit breaker is usually designed to operate even during most worst fault condition. Most worst fault condition means usually we are only discussing about symmetrical shunt faults. Okay, we will be discussing only about shunt faults. Okay, in shunt faults, what is the condition? Current value will increase. So we will be designing for the most worst fault means highest value of current possible. Okay, and in which fault you are going to get this highest current or worst fault? LLLG fault, isn't it? They are most severe fault. Therefore, design of circuit breakers is based on LLLG fault, and this is a very important, very important question for your exam. Okay, now let's begin studying about symmetrical fault, and we will study how to analyze. Okay, analysis of symmetrical fault. Okay, in symmetrical fault analysis. Okay, so let's see what happens actually in a symmetrical fault. Symmetrical fault is otherwise also called as a balanced fault. We know this thing. Okay, why do you call it a balanced fault? Okay, currents and voltages in all phases are equal. Okay, currents and voltages are in all phases are equal in magnitude. Okay, equal in magnitude, as well as they are exactly displaced by 120 degrees. Okay, this is the condition for any balanced three-phase system. Okay, balanced three-phase system will have this property. Okay, therefore this fault is also called as balanced fault. Okay, this fault is also called as balanced fault. Okay, so symmetrical fault analysis, okay, is done in two states of power system operation. Okay, power system is said to be operated under two states. What is the two states? One is unloaded state, one other one is loaded state. Unloaded means when the power system is operating without any load before the point of occurrence of fault. Okay, before the fault occurrence. And another state is the system is loaded before the fault occurrence. Okay, we will be considering the state of operation of the system before the occurrence of fault. Okay, before the occurrence of the fault, the system might be unloaded or might be loaded. Okay, we will be analyzing in these both cases. Okay, we will be analyzing the symmetrical fault in a power system in these both cases. However, for your gate exam or most of the exams, the unloaded case is very important. Okay, unloaded case is going to be very important. However, we will be discussing the loaded case also. Okay, there are very few questions in one or two questions in from the previous gate questions regarding loaded case of fault occurrence before the fault occurrence, but mostly unloaded case is going to be very important. We will be discussing, don't worry. And symmetrical fault analysis involves determination of fault level, something called as fault level or short circuit capacity, which is measured in MVA. Okay, the MVA in the power system. Okay, determination of fault level or short circuit capacity in a power system is what basically symmetrical fault analysis is concerned about. Okay, this fault level or fault level short circuit capacity is nothing but the specification of a circuit breaker. Okay, You can also say it is also the specification of the circuit breaker. Okay, fault level or short circuit capacity is nothing but it is a specification of circuit breaker. Okay, and it is measured in MVA, megavolt amperes, and also in the last class we have already seen that fault analysis involves determination of voltages and currents during fault. Okay, during fault, and using this voltage and current, what we do is we will find out the short circuit capacity. Okay, now these steps are going to be very important in order to find the short circuit capacity. Steps to find what is called short circuit capacity. Okay, so first thing is what you have to draw the single line diagram of the complete network indicating all the voltages and power ratings of the components. Okay, and power ratings of all components. Okay, power ratings are usually given in a power system in terms of megavolt amperes. Okay, and voltages are usually given in terms of kilovolts. Okay, please remember this thing. And also choose the base values, convert all the components in a single line diagram into a per unit impedance diagram. Okay, into per unit impedance or per unit reactance diagram. What is per unit impedance or per unit reactance? We know impedance Z is equal to R plus Jx. Okay, mostly in analysis of power system, any analysis of power system, we take R to be 0. Then impedance equals to reactance, right? So if resistance of the system is considered to be 0, then the impedance diagram becomes a reactance diagram. Okay, and all those values are mentioned in per unit. Please remember per unit. Okay, we will be doing only on per unit basis, not with the actual values. Okay, why per unit, why not actual values? I will make a separate video once on per unit system explaining everything about per unit system, then you will understand why we will go that. But for now just convince that we are going to study only on per unit basis. Okay, after doing this second step, now let's proceed to the third step. You have to obtain the Thevenin equivalent from the fault location. Okay, first thing is you have to determine where the fault has occurred, and taking the fault terminal as the load terminals, you reduce the remaining equation or remaining network into a Thevenin equivalent. What does the Thevenin equivalent consist of? It consists of a voltage source in series with a impedance ZTH, Thevenin impedance ZTH. Okay, like this. This is the VTH and this is ZTH, and this is nothing but the fault terminals. Okay, fault terminals. You have to find out the ZTH, VTH, and then create a fault at these terminals. Okay, create a fault at these terminals. Then what happens? Then the fault current, or that is called as short circuit current. Okay, short circuit current will be flowing through the fault. Then you can find out what is the ISC. Okay, this is not ITH, this is ISC. Short circuit current, it is also called as the fault current. Okay, fault current is equal to VTH by ZTH. We all know this thing. Now let's begin our study regarding the short circuit capacity. Now let's define what does short circuit capacity means. Okay, the short circuit capacity of a bus is defined as the product of the magnitudes of the pre-fault voltage. Okay, pre-fault voltage and post-fault current. Please remember, keep in mind, pre-fault voltage and post-fault current. Okay, product of pre-fault voltage and post-fault current. Why pre-fault voltage? Why not fault voltage? Why? Because under fault conditions, okay, under fault, okay, voltage will become zero. Voltage will become zero. So with zero, you cannot find out the short circuit capacity. So we will be considering the voltage exactly before the occurrence of fault. So that is pre-fault voltage. Okay. This short circuit capacity also known as the fault level. Okay. Short circuit capacity SCC is equal to pre-fault voltage in kV. If you are taking it in kV, and post-fault current if you are considering in kilo amps, then short circuit capacity is given by this formula. Okay. V, okay, O is pre-fault voltage and IF MVA. Okay, because this is in kilo and kilo into kilo mega. Okay, now let's consider a system is having some voltage KVB as its base voltage. the pre-fault voltage will be nothing but same as the Thevenin's voltage, and that Thevenin voltage I'm assuming to be equal to the system base voltage. Okay, all these three voltages are same: pre-fault voltage or the system voltage or the Thevenin voltage of the system. Everything is considered to be same, and I am also assuming SB as the base MVA of the system. I am assuming SB as the base MVA of the system. Okay, and we have already defined that short circuit capacity is equal to, okay, pre-fault voltage into post-fault current. Pre-fault voltage equal to VTH, therefore VTH into IF. Okay, and we have also seen that IF is equal to VTH by ZTH. Okay, so I am putting it here. I get VTH square by ZTH like this. Okay, so from this, okay, now I want to find out what is the per unit impedance of that circuit. Okay, for the Thevenin equivalent circuit. Okay, we are only studying on this Thevenin equivalent circuit only. Okay, so in this Thevenin equivalent circuit, ZTH is there, VTH is there. I want to convert this ZTH into Z per unit, okay, per unit value. So what will be per unit values will be equal to actual value. What is actual value? ZTH by base impedance ZB. And what will be the value of ZB in this system where SB is the base and KVB is the voltage base? Then we know SB will be equal to, okay, KV base square by Z base. Z base will be equal to KV base square by S base. Okay, please remember this formula. And I'm putting it over here. Then I get this value. Okay, I get this equation, this term, and I will transfer the Z per unit on the RH side and KV base on the LHS side. So finally, I get short circuit capacity as this equation. Please remember this equation is very, very important. Very, very important. Okay. Okay, we are main purpose is to determine the short circuit capacity, and this is what the formula for short circuit capacity. What is the short circuit capacity of a system? MVA, okay, base MVA or SB, what I have written here, by Z per unit, okay, up to the point of fault, up to the point of fault. What is the impedance up to the point of fault? ZTH, no? Thevenin's impedance I am taking in per unit, that's it. Okay, please remember. And also similarly, if you are supposed to find IF, okay, fault current in per unit, okay, that will be also equal to the, okay, base current of the system by Z per unit up to that point. Okay, this is also very important. Please, please, please keep in mind. Okay, there's nothing different between them. They are more or less alike. Okay. Next case is we will be studying a very important condition, that is we will see the behavior or symmetrical fault analysis under unloaded case. Okay, this is the first case. Okay, and the second case would be the loaded case. We will see that one also. So we will see what happens when a symmetrical fault at the terminals of a three-phase alternator will take place. Suddenly three phases will get short circuited. So what happens? So we will see what exactly happens before the occurrence of fault. Before the occurrence of the fault, we are already saying that the system is unloaded. Unloaded means the armature current will be zero. Okay, and the internal EMF generated will be equal to its terminal voltage. Okay, we know everything. We know these things already. And what happens after the occurrence of fault? Okay, current value will be suddenly raised. That is what we call as fault current or short circuit current. And terminal voltage will be become zero because the fault occurs at the terminal. Okay, and that fault voltage will be equal to zero, and the entire internal EMF generated will be utilized to circulate the fault current. Again is the reactance of the system. Okay, reactance of the machine. Okay, machine reactance. And one important property is, okay, during fault, okay, during fault, okay, reactance X of the alternator, okay, of the alternator is not constant, is not constant. Okay, it is variable quantity, it keeps on varying. When the fault occurs, basically this particular reactance is a variable quantity, it varies. Okay, it varies at different points of time. It will be having different values. We will be seeing that in the next slide. Okay, so when basically this symmetrical fault occurs in a terminals of a three-phase alternator, this is the oscillogram. Okay, oscillogram oscillogram graph of the fault current. Okay, oscillogram graph of fault current. Okay, see how the fault current is there. Initially when the fault has taken place, the fault is having a very high value. Okay, and that period is called as a subtransient period. Okay, the period immediately after occurrence of fault is called subtransient. Here current was high, and then slowly the current is decreasing, the magnitude of current, and this period is called as a transient period. Finally steady state period has came into picture. Okay, and let's these three distinct time periods. Okay, so there are three distinct time periods in this oscillogram. Okay, first period is called as subtransient period, and this is the period during two cycles. Please remember, SSC JEE IES aspirants. Okay, okay, important. And current magnitude is very high. Okay, it very high. And another property is current decays very rapidly. Current decays rapidly, and this current is called the subtransient current. Okay, and the reactance offered in this to this subtransient current, it will be very least. That is the reason why the current value is so high, and this reactance is called subtransient reactance, denoted by xd dash dash or double prime. Okay, please keep in mind. Next thing is transient period. Okay, and a transient period, after these two cycles up to next 20 to 30 cycles is going to be a transient period. Okay, here also current value is high, but not as high as this previous case. The current magnitude is decaying slowly. Okay, somewhat slowly, whereas here it decays rapidly, here it decays somewhat slowly, and this current is called the transient current I dash. Okay, and the reactance offered to this current is increased a little. Okay, previously the reactance offered is least out of all conditions. Now the reactance has been little bit increased, and this reactance is called as xd dash or transient reactance. The reason why the reason because the reactance has been increased, the current magnitude has been decreased. Okay, okay, whereas here reactance is least. If reactance is least, automatically current will be very high, isn't it? Now next final state is called steady state period, or this is normal period. Okay, normal state. This is the normal state of the alternator. Okay, this is when the current reaches its steady state value and the current value remains constant, does not change. Whereas if you see the transient period, the current was decaying rapidly, here decaying somewhat slowly. There is a change in value of current, but here it remains constant throughout. And the current value is less, isn't it? We have seen already in the picture. And now the reactance is called as steady state reactance, or something called as synchronous reactance, or my picture is obstructing, that is called as direct axis reactance xd. Okay, it is denoted by xd, please keep in mind. Okay, now we have seen different types of reactants now in this present, in this alternator. Now we will study in detail about these different reactants. The first important reactant we have seen was the first reactance we will be seeing is synchronous reactance. Okay, synchronous reactance is the normal steady state reactance. It is also called as steady state reactance or direct axis reactance. Okay, it is essentially the combination of winding leakage reactance and the reactance due to the armature reactions, which is also called as armature reactance, and its value is given by the internal EMF by xd. Okay, internal EMF by xd, assuming that the fault impedance, okay, fault reactance or fault impedance is equal to 0. Okay, zf is equal to 0. What is zf equal to 0? See, we have already seen this is the Thevenin equivalent of that circuit, and say a fault has occurred at this point, isn't it? The fault occurs at this point, but fault by occurring, it has also introduced some reactance or some impedance xf, and this is the already existing in the system xd, and this is your internal voltage of your generator. Okay, now what happens due to the occurrence of fault? You get a current, right? Fault current. In this condition, we can also define fault current as E by xd plus xf. Now our assumption is based on that xf is equal to 0. Therefore, E by xd is going to be your current. Okay, and xd will be equal to winding leakage reactance plus armature reactance. Next case is subtransient reactance. Okay, in subtransient period, this reactance will come into picture. What happens in subtransient period means the damper windings. Okay, and the synchronous machine will have damper windings, right? And you also have something called field windings for your field, rotor field. Okay, these windings will also set up some induced current. Okay, they will also induce some currents. Why? There is a relative motion between them and the RMF, rotating magnetic field, because the rotor is oscillating. The reactance offered to these currents in their windings are called these. Okay, they are called the damping reactance, damping winding reactance XDW, and the reactance in field is called XF, field winding reactance. Okay, okay, and these reactances are modeled in parallel with the armature reactance XA. You see here, this is the XL, okay, this is XDW, and this is X field winding, and this is the armature reactance. Now they are modeled in parallel. Okay, the overall XD dash dash, okay, subtransient reactance will be going to equal to XL plus parallel combination of XA, XF, X damper, X damper winding. Okay, this is going to be the value of XDW. Please remember this formula also. In competitive exams, they might directly ask you to point out the correct formula. Okay, and the subtransient current is going to be this. Okay, internal voltage by, okay, pre-fault voltage by the XD dash dash. Now we will see the transient reactance, which is XD dash. Okay, XD dash. So this occurs at the end of subtransient period. What happens is the damper winding induced currents will be reduced to 0. Now the remaining reactance or the effective reactance is called as what is called transient reactance. So earlier there used to be this damper winding reactance. Okay, now this became 0 because currents have been leaked in damper winding, and this is the remaining reactance. Okay, XD dash, I can write it as XL plus parallel combination of XA plus XF. Okay, please remember what will be there in what period, what reactances. Okay, and this is the value of transient current. Okay, and okay, final conclusion is the reactance during subtransient period XD dash dash will be less than transient reactance is less than the steady state reactance. Okay, what is this XD dash dash subtransient? Okay, this is the case of transient. Okay, this is steady state reactance. Okay, subtransient reactance is always less than transient reactance, and this is always less than the steady state reactance. What happens if the reactance decreases? Okay, because fault current is always inversely proportional to the reactance. If reactance decreases, fault current will increase. So current during the subtransient period will be high as compared to transient, and as compared to the steady state. Okay, please remember these relations. Okay, please remember, please remember. Okay, please remember. Okay, all right, and then mm, so you just go back to the oscillogram. Okay, in the oscillogram you got to find current magnitude is decaying like this, right? Okay, when the current magnitude was decaying, right, there was a line which was extrapolated corresponding to the subtransient, right? It was intersecting the y-axis at A, and when they were extrapolating the transient part, the the curve was meeting at B, and the steady state part, okay, the steady state part actually will be meeting the x-axis, y-axis at say point C. Then from these values also, okay, from this graph also we can determine the value of I dash dash and all these things. Okay, I dash dash is nothing but the RMS value of subtransient current is given by OA by root 2. OA is the peak. Okay, OA, what is OA? OA is the peak value of the current during the subtransient period. So peak value by root 2 will give you the RMS. I dash, okay, RMS value will be OB by root 2, and transient steady state value will be OC by root 2. Okay, please remember, please remember. Okay, now we will study our next case. Okay, that is the loaded case of an alternator. Now if it happens, what happens? Okay, now what was the condition before the fault occurrence? Okay, so before the fault, alternator is supplying some load current. Okay, I'm saying this is as I naught. Okay, and at terminal voltage will be V. Okay, voltage at terminal will be will be V. Now, after the occurrence of fault, what happens? After the occurrence of the fault, the internal EMF will be changed. Okay, why it will change? Now you see, okay, internal EMF. Okay, now after occurrence of fault, there are three periods: subtransient, transient, and steady state. Okay, subtransient period fault condition will be given internal EMF. Okay, the internal EMF which will supply the fault. Okay, that is supplying the fault will be the terminal voltage V plus. Okay, J pre-fault current, that is the load current, into subtransient reactance, please remember. Okay, and the subtransient period current is going to be like this: E dash is equal to pre-fault voltage at the terminal plus I naught into XD dash, and pre-fault voltage V plus I naught into XD. Okay, this is going to be the current internal EMF during steady state period. Suppose, okay, this is the, we are studying as an alternator. Okay, for synchronous motor. Okay, if you're going to do the same analysis for synchronous motor, what happens means the symbols will change. Okay, the E dash dash would be equal to, okay, V minus J I naught XD double dash. E dash will be equal to V minus J, okay, I naught into XD dash, and steady state voltage, internal voltage will be equal to into I naught, okay, J I naught into XD. Okay, please keep this in mind. Okay, however, this synchronous motor is not going to be important for your exams, but just telling like that. Okay, so okay guys, that's it with this session, and in the next sessions, okay, in the coming up sessions, what I will be doing is I will be detailed problems will be, so okay, I will be discussing about in detail about problem solving. Okay, and this is what will be discussed. Okay, and this discussion will be carried out from previous gate, IES, or any recruitment exam papers. Okay, previous questions of gate and all these things, and also some selected questions. Okay, selected questions from standard textbooks of power systems, and also the most important things is the questions that is demanded by you. Okay, questions demanded by you. How you are going to demand me? Immediately after watching this video, comment as soon as possible. Okay, comment in the comment sections, or otherwise mail me here. Okay, this is my mail ID, or you could also WhatsApp me the picture of the problem which you are facing difficulty and you want me to solve in the next video or the next coming up sessions. Okay, do it as soon as possible, immediately after you finish watching this video, guys. Okay, I will be discussing that because I will be doing some problems. What if I could not address the problem you are facing? So just tell me what is the problem you are facing. I will be covering them always, everything in a sequential manner. Okay, before I make the next video, I want these inputs from you. Okay, thank you guys, thank you so much. And before I start doing my next video and upload it, what you have to do, don't forget to subscribe this channel for more videos, and also do follow me on Unacademy. Like this video, share this with your friends, comment your opinion, and any suggestions are welcome, as well as know what you have to comment your questions. Okay, comment your problems. Okay, your problems, don't forget. Okay, and finally have a nice day because you have watched my video. Bye.